afternoon, and welcome to the next concurrent session of the day, making math more user-friendly, metaphors and connections to help student retention. Our presenter today is Melinda Clardy. Melinda Clardy is an assistant professor of mathematics at South Louisiana Community College, who's passionate about student learning methods and finding ways to make math more approachable. If you have any questions for the presenter during the session, please feel free to enter those into the Q&A box at the bottom of the Zoom room screen, and we will address those at the end of the talk. On that note, I will hand it over to our presenter.
Thank you for that warm welcome, Ms. Victoria. And hello, everyone. Thanks for coming. I'm going to go ahead and get my presentation up here for you to see. Beautiful. Okay. So in general, I know that probably most of you are math teachers who are interested to hear and collaborate with some new ideas, and I'm very much looking forward to that at the end. Making math approachable is, I feel, one of the hardest things about teaching math. It's so hard to feel like your students are engaging with you most of the time. It just feels like you're talking at them, and nobody enjoys doing that. So what I hope to do today is to talk about a couple of different things that I've used in my classes with good results, and hopefully hear a couple of your ideas as well. So without further ado, the first seems obvious, but is something that we maybe neglect. Those who don't learn from their history may be doomed to repeat their math class. Sometimes just talking about how these ideas originated and how the semi-average people who discovered them came about doing so. Using anecdotes can make class more engaging. It gives them a little breath of life into their usually tired math facts. Making these connections can really help to give students a chance for something else to hold on to. Oftentimes, it's not the lectures that I remember the most from my professors, it's the amusing stories they shared with me or the jokes they told. So I try to keep that in mind when it's coming to my classes as well. So with that, I just kind of want to point out a couple of easy ones, especially right now in the pandemic. It's so fun to talk about the fact that Sir Isaac Newton discovered most of his findings while he was on break from university due to the plague outbreak. So it's a fun little challenge to give them to see if they want to invent a new branch of mathematics while they're in lockdown here. Strangely enough, none of my students have really responded to that challenge, but it was still an interesting one to make, and I did get a few smiles. So especially important for a lot of levels of math is the Cartesian coordinate system. Some of you may be familiar with the history of René Descartes, and some of you may not. Depending on which story you follow, it has been said that his discovery of the Cartesian coordinate system was tracking a bug. Now, depending on which telling of this you hear, it was either because he was a very sick child watching a bug on his bedroom ceiling with nothing else to do, or because he was drunk one night in a tavern and looking at the hotel ceiling. So whichever of those stories you'd like to share with your students, the point is that originally the bug is at the origin. We call that 0, 0, and we follow the bug's movements by describing the left and right changes. So in this case, the bug is now at 3, 0 because he has moved over 3 tiles. Then the bug may change direction and head south. In that case, we would then show that negative value to indicate that there was a change in direction downward, and those positives and negatives help tell that tale. So it helps to be able to discuss what these points could be used for, especially discussing things like drafting and GPS coordinates and everything that go along with this that were used after this. And it helps to make everything a little bit more tangible instead of just something that they feel like they have to do. This also means that we can start talking about function transformations. If we have an original function and then it has been translated, we can segue into function notation and of course the coordinate geometry, if that's where we're trying to go with this as well. So making those connections back to what we do know, that Cartesian coordinate system, or making connections even further back if that's what they don't know, can really help to cement all of this knowledge and make it last. Because the thing about math that most students will say if you talk to them is, I remember it really well for the test and then it's just gone. So if we can connect something, ground it to something else that they have held on to, it gives it a chance for that knowledge to really flourish and become a part of their life, which is ultimately what I hope all of our goals are. Um, it also sometimes helps to get more hands-on with the material. Now I teach college students myself, and I can say even this activity for them is very engaging. I know a lot of times as adults, we seem indifferent to things and we don't really want to take part, but something as simple as a plastic ruler and a bag of cubes can really make the difference. We were talking about mean the other day, and I had them all get out these plastic rulers. I bought a bundle of 10 of them or something. And we put the little cubes on there, and we were able to say, well, if we don't have anything on the ruler, it balances halfway, 6 inches, because I had a foot long ruler. And then putting the objects at the fixed values would help us to figure out what the midpoint between single values were, or in fact, the mean in a set. And they had a lot of fun visually demonstrating outliers by flipping everything off the end of their ruler when they got done and then cleaning it up because that was their adult responsibility. But it really drove home the point about what makes something an outlier versus just a more extreme value too. Was it enough to really send it all toppling down, or was it just kind of tipsy now? And it gave us a segue into that, 5 number summary and actually determining whether something was an outlier using our IQR formula and everything as well. And again, just tying something back to something they experienced like that is going to make it last that much longer. And it made the discussion so much richer because they were talking about, oh, well, I bet you can't get them to balance like this. And we're discussing, can you have 90% of your values above the mean? What does that require? And it really made for a more interested class than I had seen before. So highly recommend something like that. Um, Changing gears a little bit, sometimes it's not even about making something more fun or telling a story. I know that that's not always everyone's cup of tea. And for a long time, it wasn't mine either. I felt like I was getting out of my comfort zone if that's what I was doing. But one of my kind of ease in moments was when I was discussing the relationship between the greatest common factor and finding a least common denominator. So you do have to believe a couple of things to follow with me on this at first, which is that least common denominator is difficult for most students to find. They don't necessarily click with it. It's not something that most people just see. But finding something that numbers have in common is usually easier for them to do. And working up to the greatest common factor from that is not too bad. So in general, we can use a common factor, ideally that greatest common factor, to find a common denominator. And in fact, the least common denominator is relatively easy to obtain. So let's see how. If we start with two fractions, 16 and 36 have relatively large denominators, and we would not want to just watch the students multiply those together and struggle needlessly. Having experience, we can usually see what we should be using as our common denominators, but it's difficult for someone to just jump from 0 to 60 and understand exactly what they need to do. So what we would observe here is that we can find the greatest common factor of these numbers, which is 4, relatively quickly. And that resulting factorization shows us that if they both already have 4, we don't need to multiply by that again. We can make a smaller common denominator if we just multiply by what each one is lacking. So we would multiply the first one by 9 and the second by 4 so that each of them has 2 4s and a 9. This means that the common denominator is that product, 144, and we can make our equivalent fractions. So we have each of those multiplied on the top and bottom by the required factor, and we have the equivalent fractions, which means all we have left to do is add. As an added bonus, we already know what the factors of our denominator are, 4 and 9. So we need only to check their prime factors first to see whether this can be reduced further, which it cannot. So this gives them a way to kind of see that thread and pull it all the way through so that they know what they're looking for at any given point and they can make that connection for themselves. So let's try that again. We have an even bigger denominator, starting with a 144 and a 54 here. So again, we want to look for that common factor, but it may not be as straightforward. So this time I would encourage the students to probably find their prime factorizations. This allows them to simply highlight which things match in both lists and find that the greatest common factor is 18, which is not something we think to divide by naturally. But once we take the remaining factors and give our kind of factorization as before. So we can see that we have that 18 in common and we multiply by what each one lacks, the 8 and the 3. This means that we have our common denominator, that product 432, which again is not a number that I think most of us would jump to naturally. But we make our equivalent fractions by multiplying by what each one lacked, and we can now add those up. So once again, we know that 2 and 3 were the prime factors of this denominator. So we can just go ahead and say, does 2 or 3 divide into 89? And here's where I would usually talk about reminding them those divisibility rules, seeing whether a number is even to tell if it divides by 3, or by 2 rather, and then whether the digits add up to something divisible by 3 to check that one. So in this case, we can see, well, A, it's 1 below 90, which 3 goes into. So we know it's not going to be able to do that because it's only 1 away. But B, if we add that 8 and 9 together, we get 17. And our base 10 number hack tells us that that is not going to work with 3. Awesome. So usually working out a couple of these on the board and letting them take an active role in those steps will mean that my students are more comfortable finding those common denominators on their own. And in fact, once they get to the 3 fractions being added together, that they feel more comfortable trying to find that common denominator for all of them than I was seeing my students be in the past. So that was very encouraging to me. All right, now this one's a little silly, but a metaphor that I have used in my class is to consider a radical and the reducing of that radical as a prison break. So we see that there are different orders of radicals, and those would be the different security levels of prison. So what we're going to do is look at an example of that really quick so that we can kind of see what I mean about finding that set. All right, so imagine we have the unassuming square root of 50. What we would want to do is simply find what this breaks down to at all. So they're using the same prime factorization skills that they used in the past. So we can see that that breaks down into the 2 and 25 and then 5 and 5. Now, because this is a basic radical, it is that square root implied, we're going to be able to say that what we need is a team of 2 to make a break for it. Here we go. Our partners are ready to make their escape. However, we know that this is a dangerous prospect, so they never both make it. I usually spin some kind of tale about, guard dogs or a moat or something, and everybody kind of chuckles to themselves, but it means that later they remember this, and that's what really matters to me. I'm not as afraid as I once was about making a fool of myself if it means they remember. So we have our 5 come out. We can see that on the outside, the 1 survivor, 5, and then the 2 who never had a partner is stuck inside. And again, if we keep that kind of story thread all the way through, they have that kind of understanding of what makes sense as an answer. Why do I keep the 2 inside? Why does the 5 come outside? And it answers those questions for them on a level that they feel more familiar with. And then we can go on and talk about some of the math theory if we want to, but no matter what, they've got something to fall back on if they need it. So let's try a higher security prison, all right? So in this case, we need a bigger team to make the escape because there are more hazards in our way. So we need, somebody who knows such and somebody who knows something else. So we break down our factors as before, and we find that our team of 3 is ready to go. So one of them is going to make it out. The other 2, they knew the risks and they were out of here. So the 3 that never had a partner in the first place is still inside. All right. If we're ready for a 4th order radical, we begin as before with our factorization. And you can see this tree has gotten pretty ridiculous if we start going out to the prime factors every time. So this is where I start talking about, oh, well, sometimes if you know squares or cubes, it's a shortcut. And then that sounds exciting because then that's less work, right? So even though I'm making them memorize something else, it sounds like it was their idea. So when we look at this, we see not 1, but 2 teams of players on the board. So in this case, there's going to be a 2 and a 3 that escapes, as well as a 2 who stays inside because he didn't make the team on that cut. So we have a 2 and a 3 outside that radical, and the lonely 2 stuck inside. And what this means is that the ones that are outside, we make the Bible reference, if you will, they are fruitful and multiply. So we have that 6 on the outside now. Again, this gives them something to just relate back to, a narrative to tell themselves about what's going on in this instead of trying to just do it because I said to. And in general, I found that that makes a big difference, um, especially in a software kind of format where they're not feeling like they're engaging all the time. Just having something human to fall back on can be very comforting. And it means that in general, my students will send me questions outside of class, and I welcome that personally. I think that's a great thing, because I would much rather have them turn to me than try to Google their way out of their problems and potentially land in hot water for academic misconduct. So if that's something you've struggled with as well, that's something you can consider. All right, so I have one more thing I want to discuss here with you guys. And this one's going to take a little bit longer. It's a little more advanced. So the unit circle is something that has been memorized over and over for not a lot of reason. It feels like something that we need to have tattooed on our inner arms. And in fact, some students have proposed that to me and whether I would make them wear a long sleeve shirt on test day. Um, so that being another issue, of course, what we know about the unit circle is it is a unit circle, right? It has a radius of 1 and it lays on the coordinate plane so that we have the intersection at the origin. So let's take a little bit of a closer look at that. The axes then are relatively easy to label using the fact that the radius is 1. So coming out from the circle in all directions, we get our 1s and -1s accordingly, relating again back to that Cartesian coordinate plane. So if we're looking at this, that's not very intimidating. Again, it draws from previous knowledge. So this is something that I think most students feel relatively comfortable doing, even if they're not really sure why. So at this point, what we would have them do is look at those radian measures that relate to these terms. So we would discuss possibly the idea of coterminal angles and being able to talk about positives and negative directions. One of the things I remember the best about my schooling, and I hope that somehow she sees this. My professor in trigonometry discussed the fact that the real numbers were like a spool of thread and they go around and just I don't her inflection, the fact that it felt like a human interaction, that stuck with me all these years. And I share it every time with my students because I said, even if it just means you remember me being a little bit of a goof, right? It means that you do remember this, and that means that you might actually be able to apply it when I need you to. So we see a lot of other marks on this unit circle. So let's start discussing those quadrant bisectors. So in this case, what I would relay to my students is the fact that we are talking about wedges out of this circle. And back in the day, we talked about fractions and how they were a piece of a whole. In this case, we're talking about pieces of pi, if you will. So each wedge that we see here is that pi over 4. So we can think about counting from 0, it would go pi over 4, 2 pi over 4, or pi over 2, 3 pi over 4, and so on. This allows them to just count their way around the outside and discuss what those values are, reducing as they go if necessary. After this, we have to discuss the actual trigonometry of it. What are these coordinates on the plane? So if we think about the reference triangles, which hopefully we've discussed at this point, we know that there are really only 3 values that we get. We get 1/2, we get that root 2 over 2, we get that root 3 over 2, and those are our values. And I'm just noticing the over 2s did not load up for this, so that's awesome. But the idea being that we do know that these are going to fall on those x equal y lines from, again, our previous discussion of the Cartesian plane. So knowing that these are the quadrant bisectors, we know that the coordinates must be equivalent, and therefore they must be that root 2 over 2 pairs. So once we've got all of that, they start asking, yeah, but that's only half of them, right? Let's take another look. if we look at those minor bisections, again, we want to start counting around by those fractions. So you can see everything here is marked out with that pi over 6. So it's using the axes and it's using those kind of sixth terms, and it's counting all the way around the outside. So we see our 6 pi over 6 for the pi, and then we could keep going again, like a spool of thread around and around. And they roll their eyes at me, but again, they remember that's what matters to me. So if we look at all of these angles, what we find is that we can simply reduce the ones that we must. So we'll get rid of those and put in their counterparts. And now we have our simplified version of the unit circle with those sixth terms in them. So we want to go back and think about those coordinates again. And this can be a little bit trickier because we have that root 3 over 2 and that 1/2. It's not as straightforward as saying, I know that they have to be the same, so it doesn't matter which one comes first. So again, we're going to reference back to that Cartesian coordinate system and say that for pi over 6, the x distance is longer than the y distance. They can demonstrate that, they can see that going on in this coordinate plane. And so with that being said, we can say if x is bigger than y, it has to be the root 3 as opposed to the 1, because root 3 is bigger than 1. Therefore, the coordinate pair has to be that root 3 over 2 and that 1/2. So from there, it's just a matter of repeating what we know about the quadrants, where the positives and negatives are, and understanding the kind of rotation of those points. So when we get to the pi over 3, of course, in this instance, the y is bigger than the x. Therefore, the sine value is going to be that root 3 over 2, and the cosine value, the 1/2. And so we can just keep on discussing those things. And even something as simple as saying, x comes before y, cosine comes before sine, that alphabetical order could be what makes the difference for one student to remember these things. So just establishing as many connections as you can be so vital, because we never know where that connection clicks for them. So as you can see, I'm a really big proponent of having multiple ways to do one thing, trying to simplify things as much as I possibly can. And obviously I can't talk about all of that today, and I want to hear some of your stories as well. But these are some of the resources that I've read through, at least in part, and I can definitely recommend. So Liz Strachan, I think is how you say her name. She's a wonderful author from the UK, and she had a couple of books with just some fun math facts, some divisibility rules, some little tips and tricks. And a lot of those kinds of things can resonate with these students as a way to, connect. Even something that is simple as they can do that to their friends and trick them or something. If that's what it takes to get them interested, then that's what I want to share with them. So having those little quick tips and everything, maybe you'll find something that you can work into your classroom there. So highly recommend those ones. And of course, the thinking classroom being my objective, I really try to get my students to discuss with each other what's going on. I have worksheets and activities and stuff that they do as well. But I would be fascinated to hear some of your ideas. So I know I'm a little bit fast on that Q&A, but I feel like hopefully there's going to be some good discussion here. So Ms. Victoria, would you be willing to help me with that?
Yes, absolutely. I certainly enjoyed hearing your examples. Thank you so much for sharing those with us.
Yeah.
Everyone, yes, we would love to hear your examples that you share with your students in your classroom. At this time, if you wouldn't mind going ahead and entering those into the Q&A box at the bottom of the Zoom screen. Also, if you have any questions, please feel free to enter those as well.
Yes.
I'll go ahead and pull that up here. All right. So I see we have one message about trying to enter the virtual room or the virtual booth. I'll make sure to message you privately about that. Okay, so that sounds interesting. Francine Long says she shares why pounds is labeled LBS as the abbreviation.
Oh, yes, please tell. I don't know that one. That would be fun.
Ms. Long, if you don't mind sharing a little bit more about that, feel free to take your time typing, but
Yeah, I know typing takes forever.
you definitely have inspired some intrigue here.
Yes, very much.
I personally did not know about the bug story that
Oh,
you shared, so I
my students
enjoyed
love
that.
that one. They prefer the drunk in the hotel one though. The little sick boy is sad. Drunk mathematicians are funny.
Right. Yes, absolutely.
Um, I also share usually with my stats classes the intrigue regarding why we call it a normal curve and like the
Mhm.
number of names it's had over the course of its history. And depending on how high up in math is, you don't call it a normal curve anymore, you call it a Gaussian curve. And what exactly
Mhm.
made him so special to get it named after him in the first place, which
Yeah,
is basically just being really impressive. I don't know, Gauss just did all kinds of stuff.
yes, I love that. Ms. Long shares from Libra. She has it in a project. She just Googled it.
Oh, okay, well, I'll do that too.
Good old Google.
Thank you. Thank you. I love
Yes,
it.
thank you. Um, if anyone else has anything they'd like to share, we'd love to hear it. Oh yes, SOHCAHTOA. Miss
Ah,
Cummings says SOHCAHTOA.
yes. And other mnemonics that go with that. So if you've never heard, there is kind of a please excuse my dear Aunt Sally to that one as well. And my students are always very shocked to hear that one. The some old hippie caught another hippie tripping on acid is usually enough to get them to detach from the fact they're in a math class and go, wait, what?
I haven't heard that one. That's funny.
Oh yeah, no, that one is quite an attention grabber. So yes, some old hippie caught another hippie tripping on acid. That one's a good one.
Yes, that's funny. Yes, Miss Cummings shared that as well. Thank
Nice.
you. Love to see the engagement here. Ms. Rosselli says, I also use the prisoner story for roots, but it's a war camp. So
Ah,
twos can only speak the language of other twos, etc. I like
ah,
that.
that's interesting. That's a good twist. I like it. um, one of my students really went the extra mile and tried to apply that prison break analogy to the non-real roots as well when we discussed those. And he said that the negative people in prison are the ones that change the most. So they finally come out and they're not negative anymore. They are all about, I will do this and I will do that. And so they took that extra narrative, and that was kind of fun to see.
Nice, nice. Um,
um, yeah.
Ryan Crouch says, I was taught Tom owes Andy some of his cows and horses.
That is much more PG. I like that. I like that.
Thank you for sharing, Mr. Grouch. We have some more comments. Carol Rogers says instead of FOIL for distribution, she uses walk the buffet line. It works for all polynomial distribution, whereas FOIL only works for two binomials.
That's good. I like that. I like that. I did think of another mnemonic if anyone's interested in their metric prefixes. King Henry doesn't usually drink chocolate milk, incorporates the unit there in the middle. So it gives those main three on either side. And that one, again, is enough of a what that most people will start to remember it afterwards.
Yes, I love that. Laura Rosselli says for trig, we also use all suckers take calculus for the signs in four quadrants.
Yeah, nice.
I love that.
Mhm. I've also seen people do the circle of logs complete with the Lion King introduction to discuss transforming between the exponentials and logarithms. That's another good one.
Oh,
And
wow, I love
incorporates one of the best math jokes my teachers ever told me, which was about the addition property with logarithms as well. So, but I already told one on non-PG thing, so I probably shouldn't share that one too.
that. Oh. Well, when it works, and helping people remember, right?
Yes, yes. And again, that's one of the big things for me. I don't care if they think I'm weird, as long as they remember that math. That's what I was here for.
Yes, I love it. Laura Rosselli says we use the Happy Meal analogy for distributive property.
Happy Meal analogy. You mean like the golden arches kind of thing? That kind of makes sense. A student of mine called them rainbows. So
Ms. Rosselli, could you share a little bit more about that? Just make sure we're understanding correctly.
if I misunderstood you, I apologize for taking that.
Oh, she says if you order 2 Happy Meals, you expect 2 burgers, 2 fries, 2 drinks, etc.
Oh, okay. That's better than I was thinking. That's really nice. I like that.
I like that too.
Uh,
Does anyone else want to share any stories, maybe jokes or anything that they like to share as well? These are all great and definitely creative discussion taking place. So thank you everyone for engaging in the comment box.
yes. I know most of us come to these virtual summits expecting a passive interaction. So I'm sorry for pulling any of you out of your comfort zone as well. But a discussion about engagement without engagement is just not really complete.
Right. Brian Crouch said he likes to look up quadratic formula songs on YouTube to play in class.
I thought about doing that actually. My favorite one is the Frere Jacques because it's round, so they have to sing it with you, and you actually like force your students to interact on that extra level. Um, so that one's fun. If you've never heard that one before, I definitely recommend. I also enjoyed the one with the Pop Goes the Weasel, where the little weasel actually like jumps along all of the words and stuff. That one's really cute.
Oh, that sounds really cute. Ms. Rosselli says, my very dry calculus teacher told a joke about needing to know the difference between your asymptote from a hole in the graph.
I remember a really dry teacher as well told a joke about what you call a baby eigensheet, a lambda, because that's lambda is the variable for that. Yeah, he had never told a joke, never even moved above monotone, but he told that joke. He gave one laugh to himself and then he went exactly back to what he was doing. And I will never forget it.
That's funny. Did any of the class really catch it, or he
I
just
don't
kind of?
know. I know I did. I know I did.
That's funny. That's great. Do you ever, I have a question
Yes.
to interject. Do you ever have any students who come up to you or maybe even raise their hand and just share with the class something that they came up with, and whether it is a silly song, an acronym, something like that?
I did have that student who talked about rainbows. She liked that distribution thing. It helped her to visualize what she was doing. But the I prisoner was probably the most profound statement anybody's ever made in my classes like that.
Yeah.
Um, some of the simpler things that just you said offhand to the student become part of your repertoire, I guess you could say. So for instance, with parabolas, talking about what the coefficient does, I simply say that you just have to look at their expressions. And that's kind of a fun little pun because, you know, it's a variable expression, but ultimately I draw eyes above the parabola. And the positive parabola is smiling and the negative parabola is frowning. And something just as simple as a couple dots above a parabola can transform that experience for someone. So it doesn't have to be big. It doesn't have to put you out and do all this extra lesson planning either. It's
Yeah.
just giving that one little glimpse of, wow, yeah, okay, I can remember that.
Yes, I think certainly with the parabola, I think that's a game changer. Happy and negative.
And it works again for concavity if you want to talk about the second derivative test and everything there. So, you know, further applications. And I mean, there are just so many of these. I had such a hard time paring it down for this presentation. And it's just so interesting to collaborate too. And I definitely put my email up here. If any of you want to share any of those with me, or hear more about any of these, I'm happy to do that afterwards as well. So I really hope that this can change how some of us think about our classrooms, and be inspired to be a little more creative, you know.
Absolutely. We have another comment from Miss Long. I had a student use Chips Ahoy to remember, no, I don't want to butcher this. Vux, is that right?
Oh, yeah.
And Ahoy?
So the vertical and horizontal lines. How did the chips ahoy? I get the hoy part. How did the chips help?
Can you explain a little bit more, Miss
I'm
Long?
sure, I know, I'm so bad. It's so easy to just talk and ask these questions. You have to sit there and type out long.
Yeah. Thank you for your time typing. Thank
Oh,
you
yeah.
to everyone who's been engaging in the comments. This has been wonderful.
Mhm.
She said that it's just what he used to remember.
Hmm. Now, I will say I did do some student teaching under someone at my university, and he was where I got a lot of the kind of passion for this extra step in teaching. He gave his students the continuously compounded interest formula, E raised to the RT, and he told them to write a narrative about how that function was invented. And so he picked the top one to read to the class a little while later, and it was about somebody who was thinking about math while he was in the shower using his Pert shampoo, right? And he said that when he slipped, it fell like on him, and he had that aha moment where he realized that if he wanted to have a function who was its own rate of change, he would have to invent it, and that's why he called it Pert. And of course, it was just nonsensical. The student just made that up, but it was something that, again, all of them got that little extra experience, and it was something that stuck with them, you know? So
Yes,
it doesn't always have to
absolutely.
make sense. It just, for
Right.
my workforce math class, I know that I have to teach them trigonometry because there are a lot of angles and geometry involved in what they do, but they don't really see why that would be important to them ever. So
Mhm.
for their exam, I give them a real life problem. Not to say I make them build something or make them do something, but that they were given plans for a roof support system. So full of triangles everywhere, and that they spilled a drink on it. And if they tell their boss they spilled a drink on it, they're going to get in trouble. So they're going to use the values they can still read and fill in the rest with their knowledge of trigonometry, just
Oh,
to
I
save
love
face.
that.
And so again, something just as simple as that little extra narrative to why am I making you do this problem can make
Yeah.
the difference for some students.
Oh, absolutely. That context and real life scenario definitely helps help make those stronger connections. As Carol Rogers shared, she really likes that. Thank you for your comment. Yeah, I was actually talking to my husband last night. I was telling him that I still remember the president song I learned in like fourth grade. And I mean, you don't really, I don't know, you don't have that question asked, who is the, 13th
Yeah.
president very often, but I can tell you
Yes.
because of the
Yes, you
silly
can.
song. So
And
it's
if
true.
that's what it takes, that's
Right.
awesome.
Yes, it's
So
like Toa, PEMDAS, all of
mhm.
that. Definitely remember that.
That was a fun fact I learned reading Miss Strackland's book, was that actually in the UK they use BODMAS, like BOD. And then I was like, what do the B and the O stand for?
Right.
So instead of parentheses, they say brackets. And
Uh,
then the of is what that's supposed to be. So distributing anything through those parentheses is supposed to take precedence over the regular multiplication and division then. So then I wondered, how exactly does that incorporate the exponents? But obviously reading a book, you don't have the ability to ask that to an author. So I guess I'll have
yeah.
to figure that out later. um,
Could you perhaps share the name of that book in the chat? Just
oh,
in
it's
case.
actually on the previous slide. Here we
Oh,
go.
perfect. Perfect.
Yes.
Just in
I
case
put the
it
ISBNs as well, so you can
oh,
really make
that's
sure you got it right.
fantastic. Fantastic. If anyone
Yeah.
wants to take a picture of that with their phone or maybe a screenshot, I thought that might be helpful. Perfect. It looks like Robin Cummings says, has a comment here. If you add the digits of a number and the sum is divisible by 3, then the original number is divisible by 3. This also works for 9. So 139 is not divisible by 3 or 9 because 1 plus 3 plus 9 equals 13, which isn't divisible by 3 or 9. 129 would be divisible by 3 because 1 plus 2 plus 9 equals 12.
Fabulous. That's one of my favorites as well. They also are fascinated by the 11s because most of them have seen the pattern for the single digit multiplication. But when you get up to double digit, what you say is that the hundreds place and the ones place add up to the tens place. And that means it's divisible by 11. And so they're all like, they have to try it. They have to see if they can find a counterexample. But, just that extra action puts some fire under them, So.
Yes, absolutely. Gives them the chance to review what they've learned, and definitely as they review, it's soaking in a little bit more.
It's also fun to mention, if you know the rules like the 3s and the 5s and the 2s, you can use that to talk about further values as well. So if a number is divisible by both 2 and 3, it's divisible by 6. If a number is divisible by both 3 and 5, it's divisible by 15, which is not something that you usually think about when you're doing your normal factorization. So those are some fun little easy ones that they can get for themselves when we talk about factor lists and stuff as well.
Yeah, that's awesome. Just checking the time here. It looks like we have a little bit more time if anyone else wants to share any personal stories. Looks like we did just get one more come into the chat, but definitely encourage you all to continue sharing. These have been great to discuss.
I appreciate you guys so much.
Absolutely. Carol Rogers shares, in developmental algebra, I describe the different terms as elephants and chickens. They don't match.
It's true. I go apples and oranges just to be cliche. And then my constants are money, because then they'll talk about the positives and negatives with money. Which is often something in especially remedial algebra they find very vexing. They don't know how to put their negatives together. So I ask them, if you already owe $5 and you spend 4 more, do you magically have money again? And they go, well, of course not. I'm like, well, then why would you have a positive answer? And then they're like, oh, and it makes so much sense because that extra life experience really indicated to them what made a reasonable answer there.
Yes, absolutely. Ms. Rogers also says an x squared doesn't match to x to combine for addition, subtraction, because they're both dogs and one is a Great Dane and one is Chihuahua. So that's not going to work on a combination.
That's cute. I like that. That's cute.
Me too. Anytime we can talk about dogs, that's great.
Yeah.
She also does that with positives and negatives.
Yes.
Ms. Rosselli says, I sometimes use the quote, forgiving a debt is the same as giving a gift for students not understanding the double negative idea.
That's a good quote. Do you know who that was by, or that's just one you've come up with yourself?
Hi, great question. Would you mind sharing that, Ms. Rosselli?
It sounds very Ben Franklin. So if it was you, extra kudos. Like,
oh, she said, I think it was Ben Franklin.
okay.
We'll go with that.
Awesome. Oh, yes. I've tried to talk about that one as well. Subtracting a negative is getting somebody to pay you back. So yes, awesome. Forgiving a debt is the same as giving a gift. I'm going to remember that one. Thank you very much. I don't want to like cut anybody else off or anything. Like I said, I could talk about this for days. I love it.
It does look like we are right at time. I'm looking down at my clock here. So I guess we will just pause here with our question answer discussion. This has been fabulous, everybody. At this time, I do want to just take a moment to just thank you, Melinda, for all of your knowledge, your personal stories and examples that you shared with us. This has been just a wonderful, wonderful session. And thank you to everyone who came today. Our next concurrent session will begin at 3 o'clock Eastern. And I'm going to go ahead and put into the chat our meeting room links here. Go ahead and do that here. And as I mentioned, in a previous session, while accessing our conference website, please don't forget to swing by our virtual exhibit hall to say hello to our Hawks team. If you will view a quick 5-minute demonstration, you can be entered to win our hourly giveaway. We have lots of wonderful prizes. Your choice of a 6-month subscription to Audible, 1-year subscription to Disney Plus, or $100 Amazon gift card. With that, just thank you so much for your time, everybody. Your engagement